In the last episode of this series, pun intended, we hinted at the use of the geometric series in understanding the Taylor series and generating functions. But what are those two ideas? Well, they're both essentially infinite sums of polynomials, alright, each of which has its own special coefficients attached to it. Now, there are two key differences, however, between Taylor series and generating functions. The first is that Taylor series coefficients are derived by taking successive derivatives of a function at a certain point. That's what the first equation here is showing. It's saying that the Taylor series of a function f, which is continuous, at a, is going to be 1 over n factorial, and the successive derivatives, the nth derivative in kind of detail, evaluated at that point a times x minus a to the nth power. Alright? While generating functions start with a sequence, alright, rather than a continuous function, so they're discrete, and they encode that as coefficients of a power series, and then we hope to find a closed form that's more continuous. So you can see that this is they're going opposite directions. We start with a continuous function and go to a discrete series. While here, we start with a discrete series and try and make our way to a continuous closed form function. So that's interesting to note. Now, the other big difference is that the Taylor series worries about convergence, which we also talked about in the last episode, a lot more than generating functions do. And that's because Taylor series are mostly used in approximating functions and numbers of functions and their values, while generating functions are way more abstract and are used rather than actually computing certain values. They're used to derive certain identities and formulas. All right? So in that way, we can look at the definition of the generating function as such. The generating function will take in two inputs, those being a sequence g sub n, all right, and the dummy variable x, and it encodes them as the infinite sum as n goes from 0 to infinity of g sub n multiplied by x to the n. And this is the generating function form. I'm going to call it the GF form, all right? And that can be expanded out of the sigma like this, essentially. You have g naught times x to the 0, which is 1, plus g1 x to the first power, plus g2 x to the second power, plus big O of x cubed. Now, what is big O of x cubed? Don't be afraid of this. All this means is that it's just the collection of all higher order terms of order x cubed and higher, all right? So this is called the expanded form, or the long form. All right, and forgive the terrible handwriting, but there we go. And we wish to turn this into a closed form, which is to be a function of x called g of x. All right, so we can call that the closed form. And in this way, we can look at a specific case of generating functions as Taylor series, where right here is our example, where we're encoding essentially in a generating function the dummy variable x minus a as a constant, and the coefficients themselves are nth derivatives of f evaluated at a divided all by n factorial. So that's the important distinction there. All right, so let's take a look, and we can now essentially play around with different sequences that can form different generating functions. Let's start with the simplest sequence of all, the sequence 0, 0, and just forever on zeros, the 0 sequence. So g sub n is equal to 0. And when we encode that into our sum, everything goes to 0, and so the closed form here is easy. It's just 0. Not very interesting. What gets interesting, though, is when we look at 0, maybe 1, 0 for the rest of eternity. What happens here? Well, all terms except the x to the first power term are 0. So the closed form here is simply x. And then we have the function, for example, or sequence 0, 1, 1, 0, 0 for the rest of time. All right? This just means we're picking the x and x squared terms together. So x plus x squared. And in this way, all polynomials have this sort of binary sequence associated with them when they're a generating function. That's cool because we can now turn on and off certain values in a generating function by altering parts of the sequence. But what if I did, for example, 0, 2, 2, 0 for the rest of time? What happens then? Well, that's just saying take x and multiply by 2, so 2x, and then take x squared and multiply by 2, so 2x squared. All right? And we can factor out the 2, and we get x plus x squared, which is what we had right over here. And in this way, you can essentially take a constant out and factor it out of a sequence. And so this is equal to the same thing as 2 times the sequence 0, 1, 1, 0, on and on and on. And that's essentially the first property of generating functions. It's linearity, all right? You can take a constant out of this infinite sum, all right? If you had a 2 here, you can hop the 2 out because it's a constant. It's not affected by anything. So that's the one important property, all right? And the second important property of linearity is this, all right? The idea of addition and subtraction. So I'm going to take these two ideas here and reproduce them nearby. So, well, that didn't work. Anyways, let's take a look. Here we are. Sorry. All right. if we have a function a in the variable x with a sequence a sub n, and b in the variable x with the sequence b sub n, which are expressed in generating function form like this, as we know by the definition, all right, then what we get is that the sum of those two functions separately is equal to the single summation sign, the sigma, all right, of the sum of the coefficients. All right, this is expressed essentially as this over here plus or minus this over here, and that becomes the sum as n goes from 0 to infinity of quantity an plus or minus b sub n, all multiplied by x to the n. That's the next property. It's just addition and subtraction. All right, so that's important to know. Now, the next thing I want to show is a more interesting sequence. All right, let's take a look at the sequence, maybe 1, 1, 1 forever. So essentially here, right, our sequence g sub n is equal to 1, which means when we put it in a generating function, we get the sum as n goes from 0 to infinity of, well, g sub n is 1 times x to the n. But look, that's our geometric series from the first episode. So we have 1 over 1 minus x as the answer here. And that's going to be convergent for people interested in Taylor series for absolute value of x less than 1, as we discussed in the last video. So that's very cool. We can use existing closed forms, by the way, to generate new generating functions. And so let's take a look at the example of that. And let's take a look at the simplest, kind of more complicated case here, 0, 1, 2, 3, etc. All right, what do we do here? Well, this is essentially g sub n is equal to n. All right, which means when we put it in a generating function, we have the sum, n going from 0 to infinity, of n x to the n. And here is where we can also kind of manipulate generating functions by multiplying, dividing by x, and taking derivatives. So if we start with our generating function for the geometric series, which again is right here, I'm just going to reproduce that below, right here. What we can do is take the derivative of both sides. All right, and what do we get? So taking the derivative here by the power rule, we get nx to the n minus 1. So the sum, n going from 0 to infinity, of nx to the n minus 1 is equal to 1 over 1 minus x quantity squared. All right, but we want nx to the n, so what do? Well, since this summation only depends on the argument n, we can multiply the whole thing like x, or by x. And so we get the sum of n going from 0 to infinity, all right, of nx to the n, which is the sequence 0, 1, 2, 3 onwards, is going to be x over 1 minus x quantity squared. And that's really cool. So that's just an example of kind of manipulating the series. Now, what if we want to take the even parts? 0, 2, 4, 6, and on and on and on. So g sub n is equal to 2n. Well, we could just put this into the generating function right away, but we can also take advantage of linearity. We can factor out the constant here, the 2, and we get 0, 1, 2, 3, which we already know. So we can skip all the summation work and say right away that this sequence gets the closed form 2x over 1 minus x quantity squared. And that's really cool. But what about the odd part? Well, the odd part is 1, 3, 5, 7, 9, etc. All right? And that, well, we know this is g sub n is equal to 2n plus 1. So when we put it into the sum, all right, because we can't really factor anything out of here, what we get is the infinite sum, n going from 0 to infinity, of 2n plus 1 times x to the n. But notice that this is just another example of linearity. This is the addition, or the sum, of two sequences. Our first sequence is a sub n is equal to 2n, and the other is b sub n, which is 1. And we already know these two generating functions. When we split the sigma into 2, we get the 2nx to the n, which we already know is 2x over 1 minus x quantity squared. All right, and we add that to the simple 1 sequence closed form, which is the generating function for the geometric series, 1 over 1 minus x. And so just multiplying by 1 minus x on both sides here, we can then combine together, and we get 1 plus x over 1 minus x quantity squared as the closed form for the odd numbers. So that's really cool, all right? And we can also then use other identities that we've learned with summation signs to derive generating functions in their closed forms. For example, if we look at the binomial theorem from Newton, and we look at the special case of 1 plus x to the nth power, right, we can express this as the infinite sum of k going from 0 to infinity of n choose k, x to the k. And there is a secret 1 to the n minus k hidden here, but we always know that's just 1, so it doesn't matter. All right? Why infinity, though? Well, that's because whenever k is greater than n, or once k oversteps n, the combination n choose k by definition goes to 0. So it's a finite sequence. And so essentially this is the generating function encoding the sequence of all combinations of n choose k from k going from 0 to n. So n choose 0, n choose 1, all the way up to n choose n. All right? And we're embedding that with the variable x. So that's one way to think of the binomial series. All right? It's a generating function of coefficients of combinations, very simple combinations at that. So that's really cool. All right? And the last thing I want to show in this video is how we can find closed forms using recursion and other sneaky tricks. So let's say I want to take the sequence 0, 1, 1, 2, 3, 5, 8, so on and so forth, all right, and encode it in a generating function and find its closed form. Well, you may know this is the famous Fibonacci sequence where the identity that it satisfies is fn plus 2 is equal to fn plus 1 plus fn. All right, so each next term is the sum of the two previous. All right, where we define the first two terms as f naught is 0 and f1 is 1. Great. So then the generating function form of this, the GF form, is going to be the sum, right, n going from 0 to infinity of fn x to the n. And so how do we find the closed form? Well, we're going to take advantage of this famous recursion. And what are we going to do? Well, let's just call the closed form curly f of x, like this. All right? And now let's expand that into the long form. All right? And that's going to be what? It's going to be 0 times x to the 0th plus 1x to the 1 plus 1x squared plus 2x cubed plus 3x to the 4th plus 5x to the 5th, right? Plus all terms of order x to the 6th and higher. So big O of x to the 6th, all right? And now how do we shift these terms in order to satisfy this identity, all right? Well, let's multiply by x, because that's how we shift terms with generating functions. So if I multiply x here with curly f of x, we get what? We get, well, we have 0x to the 1, all right, which we can put here. You'll see why later. Plus 1x to the 2, plus 1x to the 3, plus 2x to the 4, plus 3x to the 5, plus all terms of order 6 and higher. All right? And finally, we're going to do x squared. We're going to shift it again. X squared f of x is equal to, well, here we have 0x squared, right, plus 1x cubed, plus 1x to the 4th, plus 2x to the 5th, plus all terms of order 6 and higher. And now this is very interesting. Why? Because if fn plus 2 is equal to fn plus 1 plus fn, then fn plus 2 minus fn plus 1 minus fn is equal to 0. All right? And that means that if we subtract from the curly f of x f of x, and x squared f of x, look at what happens when we arrange the terms in the order of the powers of x. If we factor them out, then 2 minus 1 minus 1 is 0, 3 minus 2 minus 1 is 0, 5 minus 3 minus 2 is 0, and so all of these terms here go to 0 when we subtract like this, all right, including this one and this one. And all we're left with is simply a 1x to the 1. And so this means that curly f of x minus x f of x minus x squared f of x is equal to x. And by factoring out f of x, the curly f of x, right, we get 1 minus x squared equals x. And therefore, ladies and gentlemen, all right, 3 dots for therefore, the curly f of x Fibonacci sequence generating function closed form is x over 1 minus x squared. All right, and so I'm just going to remind us that this is equal to the sum as n goes from 0 to infinity of f sub n x to the n. And again, for those of you who are interested in calculus and Taylor series, I encourage you to find the radius of convergence for this function and its series expansion here. And for the generating function enthusiasts, you've just learned so many amazing tools to use from this video in finding the closed form of any sequence. So go crazy out there and find your favorite sequence and embed it in a generating function and try and find the closed form. All right? It's amazing what you can do with generating functions, and we're going to get more into that in the next video. Till then.